So what is the epistemically neutral use of the term hypothesis? The key to this question is to think of the meaning of the term hypothesis as derived from its role in the practice of hypothesis testing. We need a term that lets us refer to the particular claim that is currently a candidate for testing, the subject of testing. So this is the first pass version. To call something a hypothesis is simply to say that it's a candidate for empirical testing. Now, it's important to have a term for this because in actual scientific practice, individual claims rarely entail testable predictions all by themselves. Usually, it's a group or a cluster of claims that collectively entail a testable prediction. Let me give you a simple example. This is a spring scale. You hold it at the top, you hang something off the bottom. It stretches a spring, and there's an indicator that moves down, measuring the weight of the object in grams or in newtons, which is a unit of force. So let's say that my hypothesis is that the actual weight of this brass cylinder is 100 grams. We want to test this hypothesis. To test this hypothesis, we hang the cylinder on the hook and see where the indicator settles down on the scale. Now, what's our prediction? Our prediction is that if the cylinder actually weighs 100 grams, then the indicator in the scale should read 100 grams. In other words, we take our test hypothesis and we ask, what would we expect to observe if this hypothesis was true? Schematically, what we're doing is we're constructing a claim of the form if H, then O. If our hypothesis is true, then we expect to observe O. It's important to remember that the H and the O are two different things. In this case, the H is the hypothesis that the cylinder actually weighs 100 grams. The observable prediction O is the claim that the indicator on the spring scale will point to the number 100. This is the claim that we're actually testing. What we're testing for is whether O is in fact true. So when I look at the scale, I'm comparing what I see against the prediction O. Now let's say we look at the reading, and the reading on the scale says 100 grams. Line number 1 is the prediction. If the cylinder actually weighs 100 grams, then the scale should read 100 grams. Line 2 is the actual observation we make. We look at the scale, and it says 100 grams. So we say that this observation confirms our hypothesis. Now, what if the scale didn't read 100 grams? What if it read 80 grams? We'd say that this observation does not confirm our prediction. We might say that the observation falsifies our prediction. But what exactly are we allowed to infer from this? Are we allowed to infer that the cylinder actually weighs 80 grams rather than the 100 grams that we thought? Well, we might think so, but the logic of the situation doesn't force this on us. Why not? Because that prediction, O, isn't entailed by the single hypothesis H. There are other background assumptions that we're making that we haven't made explicit. For example, if you were quite confident that the cylinder actually weighed 100 grams, then you would look for other explanations for why the scale read 80 grams. Maybe the scale wasn't calibrated properly. Maybe we didn't read the scale correctly. Maybe there are other forces that we're not aware of that are acting on the cylinder or on the scale itself that could influence the reading. What if, for example, there was a giant magnet up in the ceiling pulling on the cylinder, effectively reducing its weight? Now, if any of these were true, it could still be possible that our test hypothesis is correct. It's possible that the problem lies somewhere else, somewhere in the network of background assumptions. Now, this example points to a general feature of the logic of hypothesis testing. In general, a test hypothesis doesn't entail an observable prediction all by itself. In general, it's the test hypothesis in conjunction with the set of background assumptions that entail a concrete prediction. So a more explicit version of the prediction would be if the cylinder weighs 100 grams and the scale is properly calibrated and there are no other forces acting on the cylinder or the scale that could affect the reading, and we're reading the scale correctly, then we expect the scale to read 100 grams. Now, assuming that we've covered all the relevant background assumptions, then logically, if O is not confirmed, all we can say for sure is that one or more of the terms in the brackets must be false. Now, if I was doing a unit on the logic of scientific reasoning, this would be the jumping off point for a whole interesting discussion of philosophical issues in scientific methodology. But the only point I want to make here is how this logic bears on our usage of the term hypothesis. Notice that only one of these claims has the label H. Only one of these is our original test hypothesis. And that's typically the case, even though the logic of hypothesis testing is holistic in the sense that it involves collections of claims that together entail a particular observable prediction. In practice, only one of these claims is the one that we're actually interested in testing. In this case, it's the weight of the cylinder. It's not the existence of hidden magnets in the ceiling. Any of these assumptions could function as a test hypothesis, but in practice, what we do is single out one of these and tag it with this label, the test hypothesis. And we treat the others as background or supporting assumptions. It's often only when a prediction is falsified that we're forced to think about the background assumptions that we're making, because now they've become relevant to diagnosing the failed prediction. So I hope that this helps to clarify what I mean when I say that the meaning of the term hypothesis is tied up with the practice of hypothesis testing, and that the basic meaning is that a hypothesis is a candidate for testing. We need a term that lets us refer to the particular claim that we're trying to investigate among all the possible claims that could be relevant to an observation or an experiment. And notice that this usage is epistemically neutral. Referring to a claim as a hypothesis, in this sense, entails nothing about how strong or weak the evidence is for it. Scientists will sometimes refer to the Big Bang hypothesis, for example, and this is in no way meant to imply that that hypothesis is conjectural or tentative or not well supported by evidence. Here's an example from an article on Universe Today. The basics of the Big Bang theory are fairly simple. In short, the Big Bang hypothesis states that all of the current and past matter in the universe came into existence at the same time, roughly 13.8 billion years ago, and so on and so on. This passage is just describing the main idea of the theory. Calling it a hypothesis just draws attention to the fact that it makes a set of claims about the world, and these claims are testable. That's consistent with these claims having been tested successfully. In the next paragraph, this article says, while this is not the only modern theory of how the universe came into being, for example, there is the steady state theory or the oscillating universe theory, it is the most widely accepted and popular. Not only does the model explain the origin of all known matter, the laws of physics, and the large-scale structure of the universe, it also accounts for the expansion of the universe and a broad range of other phenomena. Frankly, this undersells just how strong the consensus is. The point is that this is a perfectly legitimate use of the term hypothesis. In fact, this usage is pretty much synonymous with the term theory, and this happens too quite often. In either case, it's an epistemically neutral usage. It's not contradicting the epistemically loaded use of the term. It's just a different use of the term. So I hope this is helpful. The term hypothesis, like all the terms that we've looked at, can be used in different ways, and they can all be legitimate parts of our scientific vocabulary.